In this tutorial, we will be discussing radioactive decay. In nature, often one radioactive nuclide changes into another radioactive nuclide. The daughter nuclide is also radioactive. The radioactive nuclides that are produced until a stable nuclide is formed are called a decay series. Radioactive decay is the rate of decay associated with a radioactive isotope. It is characteristic to that isotope. Each radioactive isotope has its own half-life. It is the time required for half of the original quantity of an element to decay. The shorter the half-life, the faster the decay. The decay can be in particular in nature, such as beta or alpha, or energetic, such as gamma or X-rays. It is constant and independent of any physical or chemical change the atom may undergo. It can be calculated at any given moment by measuring the rate of decay of a known quantity using the radiation detector. Radioactive decay is a first-order kinetics reaction, which means the rate is equal to Kn, where N is the radioactive nuclei. Which also means if we do the integrated rate law, the natural log of Nt over N naught is equal to negative Kt. The half-life for first order kinetics is 0.693 over K, K being the rate constant. The shorter the half-life, the more nuclei decay. The rate of radioactive change is not affected by the temperature. Radioactivity is not a chemical reaction. It's a nuclear reaction. So here's just a brief overview of a few of them. For instance, carbon-14, they state is 5,730 years. Uranium-238, which is what we use for nuclear reactors to do nuclear energy, is 4.5 times 10 to the 9th years. Radon, 55.6 seconds, is analyzed in this curve here. Notice that they rounded it up to 1 minute. If we have 1 million atoms of radon-220, remember it's specifically for that isotope. After 1 minute, we will only have 500,000 atoms left. After 2 minutes, that 500,000 gets cut in half again to 250,000. At 3 minutes, this number gets counted half again. And that's how half-lives work. Each time it goes through a half-life, you cut it in half. Cut the remaining in half. Alright, so let's do a practice problem. A wooden object from an archaeological site is subjected to radiocarbon dating. The activity of the sample that is due to carbon-14 is measured to be 11.6 disintegrations per second. That's going to be our NT. The activity of carbon sample of equal mass from fresh wood is 15.2 disintegrations per second. So that would be our initial. The half-life of carbon-14 is 5715 years. What is the age of the archaeological sample? So the first thing we need to do is figure out the rate constant, K, for the process. You may remember that radioactivity is a first order process. Therefore, the rate constant can be solved with this equation here. We can solve for the K by plugging in the T of 1/2 and then rearranging to solve for K. By doing this, 0.693 divided by 5715 is equal to 1.21 times 10 to the negative 4. Now we're going to take this value and plug it into the integrated rate law. So we can now determine the time. So that means that natural log of n of t and n of naught, which is what we were given in the question itself, is equal to negative kt. These 11.6 and 15.2 were given in the question. as disintegrations per second. K is what we saw for in the previous screen, and so we want to look for T. So 11.6 divided by 15.2 is 0.763. Take the natural log of this and divide it by 1.2 times 10 to the negative 4, and that comes out to be 2,240 years. Let's do another one. Calculate the mass of Pu-236 remaining after 5 years if the original mass was 1.35 milligrams. They also gave you the half-life is 2.86 years. Once again, the first thing we want to do is figure out what the rate constant is. So we need to find K. We know what the half-life is, 2.86, and we know that it's the first order reaction. So it's 0.693 divided by K. We are going to rearrange the equation and plug in the half-life. So multiply each side by K. There should be a 3 here. 0.693 divided by 2.86 becomes 0.242 per year. From here, we can use the first order integrated rate law to determine the mass N of T left after 5 years. So that means the natural log of N of T, which is what we're looking for, over N naught. They tell you in the question the original mass is 1.35 milligrams. We solved for K on the previous screen. And we're looking for time. So, let's ignore that for now. We're looking for N of T minus natural log of 1.35. We can rearrange this to be ln of nt minus ln of n naught. That's how you separate this type of equation. That's why I was able to pull 1.35 down. Is equal to the K, which is what we saw for in the previous slide, times 5 years. From here, we take the natural log of 1.35 to equal 0.3. And we take 0.242 times 5 to equal 1.21. Rearrange the equation to solve for the ln of nt is equal to 0.91. In order to get rid of that natural log, we're going to use the e to the x function on both sides. The natural log and the e to the x cancel out. So we're going to have the e to the x at 0.91. And then that comes out to be here. When you take e to the x of 0.91, the N of T is then equal to 0.402 milligrams. And that's how you solve for radioactive isotopes decay.